and thanks to the organizers for inviting me. I'll be talking about photons, and I want to start with, of course, changing my slide. Anything that I'm missing here? Great. So I just want to start with, just pointing out this very nice thing that you have, this very nice gender representation, the condensed matter and quantum information. Finally, I feel I'm in the right gender and the right attire. I really appreciate it, and I'm sure Sumathi had a lot to do with this, right? So I won't comment on the condensed matter person, but then, I really like being in quantum information as of this conference, right?
The right choice of gender.
Right choice of gender and everything. Everything is perfect, actually. But having said that, this is condensed matter meets quantum information, and I work with photons, which famously don't have matter. And so again, one of those conundrums, in how to present a talk in this conference. And so I believe, the next 25 minutes, I'll still convince you that there's a lot of quantum information that we are doing with photons. And it is a matter of using the same principles, in condensed matter and beyond, right? So that is the general idea. And with that, if you want to know more about photons, which aren't talked about much in this conference, so do have a look at some of the, textbook chapters and stuff that we have written, if you are interested, especially as a student. So I'm in the Quantum Information and Computing Lab, and this is the group. Again, I begin with acknowledging them, just in case I run out of time, because without them, there are no experiments, and without the previous people also, and so on. So having said that, this is how we began in 2012 with cutting of 3 slits, or in some sense, 3 ribbons. And some people know the significance of 3 slits so far as I'm concerned. And we do a lot of both fundamental science and applied technology, and that is how we continue. And the previous talk was very useful to me, and I'll tell you why. So this is what we do in general, all these things, but we are going to concentrate on this quadrant, which is quantum information processing, and not talk about computing, communications, sensing, and so on. But having said that, what I'm going to talk about is, 3 different experiments, just to give you a flavor in the 25-minute period. First is a direct determination of different entanglement monotones, which is used to quantify entanglement in arbitrary dimensional systems, okay? And so I'll show you an experiment where we have done this. Then go on to a new quantum state estimation tool, which is going to rival quantum state tomography. It's called quantum state interferography. And finally, a couple of minutes on experimental loophole-free violation of the Leggett-Garg inequality and the WLGI, which is the Wigner form. And the previous talk talked about entanglement, weak measurements, precision measurements, and that is exactly the theme of these 3 topics. So there is synergy, even if it's with photons, right? So why higher dimensions? So that's the first topic, and again, that was talked about previously, where we talked about qubits and the Mermin inequalities and so on and so forth. But then just to zone in on why higher dimensions are, interesting in general. Essentially, what we are doing in quantum computing, for instance, is trying to increase the number of qubits which are in a coherent superposition. So 2 to the power 50 is something, which was interesting for a long time, and now it has become 400 and so on. But then it's just about increasing this whole thing, 2 to the power something, which gives us, this access to the state space, which is very large. So now comes the point that, if I don't work on this 50 and 100 and 200, but work on the base, and try to increase the 2 itself, then I can actually deal with a smaller number of systems and still attain the same complexity of the state space that I can do with the larger number of qubits. And so that is one obvious motivation to look at higher dimensional systems. And so essentially for this, you need 2 qubits, but you can do with 1 Q quad and give the same amount of information. So this is a nutshell. Having said that, what we are doing is working with higher dimensional systems in the lab using the spatial degree of freedom of the photon. Okay, and so this is the first paper where we have actually discussed how we are making these qubits in the lab. These are bipartite qubits that we are working on. And having said that, so essentially just what is a qubit? So qubit has 2 orthogonal states, and which is in a coherent superposition. Qubit, on the other hand, will have 3, and so on and so forth. So if you think of the simple idea of a single photon incident again on, let's say, a 3 aperture system, I do not know a priori which aperture it is going to go through, so I form a superposition of all 3. And so this is one way of generating a spatial qubit, or in principle, any D. You can keep increasing the apertures, and this will go on. So there is a lot of previous work on this where people have used this technique to generate these spatial qubits and do many interesting things with it. what we came up, and this is something I did during my postdoc at IQC, where we actually played a quantum game and showed the advantage of a qubit over using its qubit counterpart and so on and so forth. But having said that, what we have come up with at RRI is a new way of generating these qubits. So instead of having a single photon incident on this aperture system, what we are doing is we are shaping the pump beam. So you have the pump beam in a down conversion process. We are shaping it using, for instance, a 3 aperture structure or a 4 aperture structure, whatever have you. So we are shaping the pump beam, and the pump itself then carries forth this sort of a structure. Okay, so instead of a Gaussian pump, we have this pump. And so when this pump is pumping my nonlinear crystal, giving rise to this pair of photons, the pair of photons carry forth very faithfully the property of the mother photon, as we call it. So the mother photon passes on its properties to the daughter photons, and these daughter photons then also carry this structure, this 1, 2, 3, and this is actually the picture, on a camera. So this is the idea of, already, yes.
Which is, so when you send in a photon, a flame wave photon,
yeah,
it will always come out in the same superposition.
No, it's not a photon. So this is a laser beam. So this is a laser beam that I'm sending it. So first of all, a laser beam is usually Gaussian in shape. What I'm doing is I'm actually shaping the laser beam and giving it a triple slit, let's say, structure for now. So this triple slit structure is carried through to the nonlinear crystal, and this is called spontaneous parametric down conversion, which gives rise to now a pair of photons. This pair of photons carries forth the same structure that the pumped laser beam had.
But there's no information.
No, not yet. I mean, we're getting there. So this is how it looks in the lab. Okay. So this is the idea. So as I said, so this is the, what will happen. So if I have a Gaussian pump, then this is how the photons would end up looking. But if I actually have a spatial structure, so this is the pump, and this is the single photon profile at the detector. Okay. So 2 single photons which carry this profile. So now comes the question, these 2 photons, which are now these 3-dimensional structures, are they correlated with each other? Going on to the first topic of last talk, which is on entanglement, what is the use of having these, 3D structures if there is no correlation? Is there any way in which I can figure out, first of all, whether there is any correlation? And so this was the first thing we did. We actually measured the spatial correlation between this pair of photons, and we found this very nice 1, 1, 2, 2, 3, 3 correlation, which means that if one of the photons is here, the partner photon is specifically correlated with this, and the rest of it has no correlation. Similarly, if it is in the middle, end, the end. So we had perfect 1, 1, 2, 2, 3, 3 correlation, and we quantified this using what is called the Pearson correlation coefficient, which is a very well-known measure in statistical correlation measures. And 0.9 is a good number if 1 is the highest for an experiment. So then comes the question, is this correlation quantum? That brings us to, again, the same topic that, is there a way in which I can measure this entanglement, or for that matter, have an entanglement witness, right? So how do I know this correlation is quantum or not? Just because it's between photons doesn't mean it has to be quantum. So what we first showed is that this correlation is not shared by the pump beam. That was one thing we already showed here. But then comes the recent work where we went on to actually measure the entanglement between this pair of qubits. Then comes the point, if you have a pair of qubits, how do you measure entanglement? So the standard way is you do quantum state tomography, and then you extract measures of entanglement. So when you have a 3x3 system, then essentially you require 81 minus 1 number of measurements. So 9 square minus 1 because of the trace row being 1. And so as you go to higher and higher D, this becomes intractable. How do you measure entanglement in a D cross D system? And so we came up with a new way of doing that. Instead of trying to do this tomography and extracting the measure, we actually related statistical correlation measures with measures of entanglement by perfect monotonic relation. So this was a theory work which preceded the experiment. And so we derived the monotonicity relation between negativity, which is a measure of entanglement, and Pearson correlation in arbitrary D. Then again, negativity and sum of mutual predictabilities in arbitrary D. And then entanglement of formation, which is yet another measure of entanglement, and mutual information, which you all know is a very well-known statistical measure in arbitrary D. So this followed, this was followed by the first direct measurement in the lab of this entanglement monotone. And we went on to find interesting things, that negativity and entanglement of formation are non-equivalent entanglement measures. And this was the first experimental demonstration of this non-equivalence. So this is the paper which I urge you to look at because it's a short talk. So, and this is the one in which we generalized this to actually mixed states. So this was for pure states. We also found the same relations for the mixed states arbitrary D. And in this more recent one, we have actually done this now for tripartite entanglement as well. So just not sticking to bipartite. So this is a series. And these are the equations for the theorists. I mean, also for the experimentalists. But then, so these are the beautiful, equations where we actually find how this negativity and this are connected. Now, these guys you can actually measure by one pair of mutually unbiased basis measurements. So instead of having to do this huge number of measurements, if you measure in a mutually unbiased basis, then you can actually do this with either one pair or even one measurement, which is what we went on to show. And that is a detail I can't get into. But then by doing one set of measurements, we are able to actually figure out the exact amount of entanglement. So this is actually better than entanglement witness, because entanglement witness actually tells you whether something is entangled or not. But here I'm giving you exactly how entangled it is. And that is useful to me as an experimentalist, because if I have an entanglement of 0.9, then my teleportation, let's say, if I want to do teleportation with it, will have that kind of fidelity. So it's important for me to know exactly how entangled it is. And we have a new way of doing that by measuring statistical correlation measures. So this is the first information, and this is, of course, a bit of detail. So this is just to tell you, that this is the 1, 1, 2, 2, 3, 3 correlation, and this is the, interference pattern. So interference actually, again, it was hinted in your talk. So interference actually captures in it an entanglement witness. So if you see an interference in the coincidence plane, that is already a witness of entanglement. But then beyond that, we are using the visibility, connecting it to purity, and then using that to actually talk about the negativity and so on and so forth. So that detail is also related to the previous discussion. So what next? Now we have this very nice pair of bipartite qubits, which are nearly maximally entangled. We know exactly how entangled they are. We are working on diffraction-based LOQI. And we have already shown the beam splitter. Now we want to show the phase shifter. Then we can use the Rex-Zeilinger protocol to come up with different kinds of arbitrary protocols for computing as well as communications. And so this is what is going on right now. And so this is the snapshot where you can see various details of various works which we have done related to this. And again, for the students, if you want a little bit of a general overview. Right. So second part is again related to interference, which of course happens to be the theme most quantum information is related to. So what is it that we have done? Now, we have used interference to actually come up with a method where we can do better than quantum state tomography. Now, quantum state tomography is something which we are all using in the lab for figuring out the state. So what have we done? Why quantum state estimation is important? Well, for theorists, it is not so important because you already begin with a form of the wave function. This is my wave function and the rest of it follows beautifully. But that is not what happens in the lab. We don't really have what we want. I mean, so in some sense, there is always an ambiguity about what we prepare and what we want. And so this we cannot assume to begin with. So we need to know the exact form of the density matrix so that we can do many things with it. And of course, the reduced density matrix is related to entanglement entropy. So that also gives us a measure of entanglement. So what we have done is we have used interference to devise and experimentally demonstrate a new method for quantum state estimation, which we call, and this is Ganpathy's coinage, quantum state interferography, as opposed to tomography. Okay, and so this is the question: can we have a device with which, without any change of internal settings, we can measure the quantum state of the system? Okay. And so there are different ways. This is tomography. This is, the CT scan. The same idea is used in quantum. You have a quantum state. You do many projective measurements into different bases, and then you stitch it together and figure out what is the quantum state. But then that actually involves, a d square, as I mentioned. Same thing, that as the d increases, you require d square minus 1 a number of measurements. So then came this idea of using weak measurements, again related, where you can actually come up with direct measurements, but follow where you have a sort of sequential measurements, one of them being weak. Okay, and so then people came up with different ideas on this, and this was the direct measurement of the wave function. This was for polarization state, and so on. So then you can see this is the weak value, and then the weak value will actually give rise to these things. And so we won't get into the details, but this is a way in which you can actually directly measure the quantum state without doing tomography. and people did many interesting things. Then these guys came up with this nice comparison between direct state measurement and tomography and went on to show that there's a lot more error in this than that. So they kind of concluded that, it is not as good as tomography. And so they left it at that. So you need something better than that. So the answer to that came from these guys where they said strong measurements give a better direct measurement of the quantum wave function. So as opposed to weak, you go to strong. And this was also a nice paper followed by experiments where they went on to do this using strong measurements. Okay? So this is the history. So there's a lot of this. So this is our work where we have actually done what? We have come up with an interferometric method with which an unknown quantum state can be measured from the visibility, phase shift, and average intensity of an interference pattern. So there is no weak measurement. It is not a direct state measurement. Essentially, it is a single short state estimation method using interference as a tool. So it's essentially something adding to the literature of already, a lot of literature using these ideas. So this is a snapshot. It tells you, how it compares with tomography. So if you have this as the dimension of the system, if you do quantum state tomography without any assumption, when you go to 100D, this is the number of measurements you would end up requiring. But for quantum state interferography, obviously the scaling is linear. So we have D-1 measurements as opposed to D²-1. And the best you can do with pure state assumption, which was shown by a different paper, is 5D-7. So naturally, we have reduced this, and so D-1 being much better than the previous, exposition. So this is the experimental setup. I'll skip that. So the general idea is that, this is your density matrix. And so if you actually can measure these expectation values, then in principle, you can measure the density matrix rho. But one of the things you may notice if you are observing carefully is that we need to measure the density matrix of this guy, and this is a non-Hermitian operator. So that brings us to this thing, how do you do something like that in the lab? And in fact, that is a question we have answered earlier, how you can measure non-Hermitian operators in the lab using weak values. Okay, again, related to this concept of weak value. And so I will basically just tell you this, that, if you have this sort of non-Hermitian operator, you can do polar decomposition and write it as a product of a unitary and a Hermitian. Okay, and for an optical scenario, it can actually be something like the sigma x and the pi 0. So this is essentially a half-wave plate at 45, and this is a polarizer. Okay, so you can replace this with essentially that. And so this is the half-wave plate, and this for theta equal to 0, this one is a linear polarizer. So by using this combination, you can break up a non-Hermitian into this product, and then you can do this measurement. And so this is what the weak value looks like. And so this, we went on to show the experiment as well, how you can measure this in the lab. And this brings in the interferometer. So instead of actually, so how do you do this in the interferometric scenario? So this is what it is. So you have the state, and here you have the, the projection, and here you have the wave plate. And of course, you do a lot more, which I won't get into for lack of time. But the intensity at the detector is this way. So you can see these terms come in naturally. So by looking at the intensity distribution pattern, you can actually figure out these quantities which you wanted to begin with to determine this unknown state. And so that is what, and so this is a bit much, I guess. So having said that, so a lot of reading for a 25-minute talk, there's a lot of reading always. And so this is what we went on to show. This is the weak value as a function of half-wave plate angle. And, it was a very nice result. But I go on to quantum state interferography. So here, this is a summary. So as you can see that tomography is D²-1, best is 5D-7 for pure state. Interferography requires D-1. So it's a, essentially incident state. You have this interferometer, and then you have the interference pattern, and you can infer the state from it. And so this is a pure state and the mixed state, how you can represent. And so again, this is the theory where essentially the idea is that by measuring the phase shift, the average intensity, and the visibility, I can get these three terms which come into the interference pattern, and then from that, I can get the quantum state. Okay, and so I'll skip we did lots of measurements, but you can see the fidelity for pure and mixed are both very good and pretty comparable with quantum state tomography. So it is in the 95%, 93% category, which is fine. I mean, nothing is ever 100 in any experiment. So we got very nice results for our state, and we did the entire block sphere. So we showed this for all possibilities and so on. And this is a neat idea, that essentially if I could miniaturize this, this is not the right audience for this is better for a company, but then ICTS, of course, is in a theoretical science institute, so I'm sure it's the opposite of a company, so it must be also better, good for this audience to realize that, we can come up with an experiment where we can actually miniaturize something, box it, and these are all components that are available actually in little sizes, so I can put in my unknown state, and then I can get out so I can carry it in a pocket. That was the general idea. And I'm not going to make this, but if there is anybody interested in forming a company, get in touch with me. And so this is going to be a centimeter long. Actually, we've done these calculations. But having said that, if you want to do this for the qubit, where the real fun begins, because that is where you have d-1, this is how, so this proposal, it's a long paper actually, so I can't go into the details, but everything is very nicely worked out. And for bipartite pure qubits also, you can actually use this. So single qubit, you can do 2 of these interferometers and you can get the entanglement from it, and a bit much. So essentially bipartite, you require 2 experimental settings and 3 interference patterns. In QSI, to quantify entanglement, we only need the reduced density matrix. This we know. And so we can do this with a single experimental setup. Whereas, of course, in tomography, it will be 9 measurements. So here also we have an advantage. Bell violation with knowledge of basis, one would need 3. So it's better than Bell as well. Okay, so it's a resource. So having said that, the last 2 minutes, I'm actually doing well in terms of time. Any questions? No. Okay, so I'll take it in the end. So I talked about the higher dimension. I talked about how we have come up with a new entanglement, a new way of quantifying entanglement in bipartite arbitrary dimensional qubits. We showed the experiment, how we did it in the pure state. We have not done it in the mixed state yet, but it is currently under review, so and so on. And we have also shown this for the more than 2-party scenario very recently in theory. Then we followed this up with actually again taking the higher dimensional theme, but now coming up with a new way of estimating the quantum state by using interference. And so essentially coming up with some sort of a substitute to tomography. If you are interested in really high D, this will come in really handy. Finally, we are going to show you an experiment where, of course, it is not a question of high D, it's again a quantum information experiment where we go back to this theme of inequalities and violation of inequalities and what they may mean, which is again a very standard scenario in many of our experiments where we use this for various witnesses and so on. This brings us to last year's Nobel Prize now, because as of this year, yesterday we have a new Nobel Prize in Physics, which is also to light. So 2 Nobel Prizes, one after the other, to light and matter physics is great for us because there's so much happening in high energy physics and cosmology and so on. We feel very pleased with back-to-back Nobel Prizes in light and matter physics. But having said that, this one is important for the talk because this was given to these people for their exceptional contributions to violation of Bell inequalities and pioneering quantum information science itself. So now, why is a loophole-free test important? I'll ask you a question. Our organizer here in the middle.
Good job.
No, because you will, right, have some question. So now why?
Speechless.
He's speechless. Okay, so I won't ask you the question. It wasn't to put you on the spot, but then why is a loophole-free test important? Got the Nobel Prize and all that, but then there must be a reason for it. So suppose you and I are having an argument, okay, and I will win the argument, right? So how will I win the argument? It is by finding some problem with yours, okay, which is a loophole. That is what happens in a court of law. So if I'm actually trying to win a case, I will have to find a fault with your argument and then I'm going to win the case. So if your argument has any loophole, then naturally that is not going to stand the test of time or law and so on. That is where loopholes come from. So now if I'm doing violation of Bell inequalities and there are alternative explanations to what I'm trying to show, then those loopholes will create problems when I try to apply this elsewhere. And so Bell inequality violation is the basis for secure quantum communication, which maybe you are aware that, the quantum key distribution, teleport, everything sort of has this Bell inequality violation as a basis. So if this is not done in a loophole-free way, then my eavesdropper can use that loophole to come up with some kind of an attack on my protocol. This is taking away to quantum communication, which we do a lot. But having said that, this sort of a loophole-free test is not just important for philosophical point of view, which also is very important that, and that things are fine, local realism is violated to the extreme, and so on and so forth. This is very important. But it's also important because I can do this perfectly secure QKD and unhackable source of random numbers. And please have a look at this article, which I didn't write. I have 1 more minute. Yeah, this is an article. Okay, thanks. So this is an article I did not write, so it is obviously a very nice article. Have a look at it because it tells you why a loophole-free test is important, especially for people towards the back, except Shorin, who are all students, right? So, so now this is our contribution to the loophole-free literature, where we have done a loophole-free interferometric test of macrorealism, okay, using heralded single photons. So I knew I wouldn't have a lot of time, so I don't have a lot of slides on this, only 2 slides. So what is the idea here? So when you have, and this again you mentioned in the previous talk, for Bell violation, you need the spatial separation, you need, and so for loophole free, you need a particular kind of spatial separation so that you're outside each other's light cone, and so on and so forth. Now, that is not very amenable if you want to, do something in a smaller, let's say dimensional, if you want to make a device, let's say, for instance, which you want to sell, if you at all want to do that, you don't want to have something which is separated by 2 buildings and using that violation. Right? So now comes the point that, if you have a single particle, how do you know whether local realism or whether, forget about local because a single particle is localized, but how a single particle, what it talks about, what is its contribution to realism? Is realism satisfied for a single particle? Or for that matter, how quantum is a single particle? How will you test the quantumness? So Leggett, Sir Anthony Leggett and Anupam Garg, they came up with, this Leggett-Garg inequality, which is actually the temporal equivalent of the Bell inequality. So Bell inequality has the space, the non-locality coming in. In this, we have time. So single particle is evolving in time. So you can have correlations between different instances of time, T1, T2, T2, T3, T1, T3, and so on, instead of space. So you can replace the space with time, literally, and you have the Leggett-Garg inequality. And so Leggett-Garg inequality is actually used as a test of, realism as well, especially for single particles, which can exist in a superposition, macroscopic superposition. And so what we have done early last year is the first loophole-free violation of the Leggett-Garg inequality. Okay, and so where we have closed all the loopholes that were known to plague these inequalities. So I would say that, so again, this has taken several decades. So many people have done many experiments to close individual loopholes, a bit like the Bell literature, but then we have been able to do an experiment where we have closed all of them. And so this is very important because now you can use this again without any inhibition for secure quantum communications, just like the Bell inequalities. And this is something we are already doing. Can't share the result of that with you because the paper is in a review in a journal which doesn't like an archive posting. So we'll see what happens. Okay. So hopefully at some point we'll have something good or bad to say, but the paper is excellent. You don't know about the journal. Okay, so this is our paper. Do have a look at it. It's a very long paper which tells you all the details about how we have closed all the loopholes. And this is our, again, interferometric setup. We have one interferometer followed by, so it's a cascaded interferometric setup and so on. And so this is, of course, something I will show in the end. So this is the, so this is the macrorealist bound. Okay, so if it's just like the 2 and the 2 root 2, here you have 1 and 0. And the quantum mechanical prediction is this. And so what we also went on to do is come up with the quantum mechanical prediction, including all the non-idealities, because it's never 2 root 2, actually, even in CHSH Bell. So if you take all the non-idealities, it will be lower than that. Any experiment is going to try and be as close as possible, but not quite because of various reasons. And so this is the bound, and this is our experimentally measured value. And to quote the previous speaker, it is also too good to be true kind of thing, picture perfect kind of thing, but it's true. So, this is our experiment and this is the theory. And we do have a beautiful match between experiment and theory. And of course, we also, got appreciation from new scientists, which called it the most watertight experiment of all time. So with that, I hope I was also almost on time. Model speaker, no? Okay.
All good.
Okay, thank you.
Thank you very much. Let's thank Urbashi. And we have time for questions. Okay, Yuval is the only one raising his hand. You have 5 questions this time?
Last time we had 4. But, okay, good.
So the first thing about the second part of your talk, what good is it to measure the weak value?
What does it, sorry? No.
What is the advantage for you in characterizing things by
In the
weak
quantum
values?
state interferography experiment?
Yes.
Yeah. So in the quantum state interferography experiment, what we went on to do, so it's a weak value, not a weak measurement. And that is something, I don't know whether you caught that. So the idea is that what we have done is we have measured the transition amplitude. So essentially a weak value is just a transition amplitude. You have a pre-selection, you have a post-selection, and you have a measurement. So we have just used that formula. So we have not done a weak measurement. In fact, the second paper that I showed you in that series of 3 tells you about how to measure a weak value without doing a weak measurement. And so we have used that. For our quantum state interferography, the weak value is not so much important. It is the measuring of the non-Hermitian operator, which we can do by breaking it up into the Hermitian and the unitary.
No, but look, I worked a little bit.
It wasn't at the weak regime.
I worked a little bit on weak values, and weak value is a protocol which involves preparation, post-selection, and so on. But part of it, one step of it, does involve either weak measurement or stock measurement with a small probability.
True.
So
No, that's very true.
but I mean, when you go into such a protocol, you always need to ask yourself, what do I gain?
That's
there
correct.
are certain examples where it's advantageous to.
As I said, we are not really doing a weak measurement in that particular paper. We are only measuring up. So it is a weak value is a transition amplitude. So the AW, as you know, is phi A psi. So essentially, instead of psi A psi, it is just pre and post. That is what all we are doing. We are not really doing it in the weak measurement regime. So there is not much advantage in our protocol. Our protocol actually tells you how to use an interference pattern to infer the quantum state. So we don't use the weak measurement regime.
Okay. Second question. Yeah. You mentioned the first part, monotone, entanglement monotone.
Entanglement monotone, yeah.
Now, this is all very nice, but as we learned from Bell and from CHSH, you have some bound such that below this bound, everything can be explained by classical correlations.
Sure.
Only if you violate this bound, then you go to a quantum macrorealism.
Yeah.
So the fact that you measure monotone doesn't tell me anything whether you have a bound and whether you exceed this bound.
If you have separable states, then negativity is 0. So the fact that we actually have measured, so anything up above 0 is going to give you a measure of, so this is the same, so forget about higher dimension. If you just talk about 2-dimensional systems, which are more common, 2-qubit, bipartite qubit scenario, then you measure concurrence, you measure negativity. So all of these are 0 for separable states. Anything above 0 is entangled. But what we are saying is that it's so essentially it's a monotonic function as a function of the amount of entanglement, and it is bounded by 1 in this case for a maximally entangled pair of qubits. So if you have 0, it is separable. If you have 1, it is maximally entangled. Anything between 0 and 1 is non-maximal. So, I mean, of course, that is how you will, so it is like, measuring any quantity. Something which is above 0 in this case is entangled. So it is not about, using it as a witness, it is about using it as a quantifier of the amount of entanglement, which is something which is commonly done in bipartite qubit. For instance, entanglement entropy is one such example, which is done in, bipartite qubits. But for qubit scenario, more common ones are negativity and entanglement of formation. That is the one which most people try to, comment on. And what they tend to do is they find the bound on entanglement. So lower bound on entanglement of formation. So they say, this is the lower bound on entanglement of formation. So that is why beyond this, it is entangled. So they use it as a witness. But then of course, for a maximally entangled pair of qubits, you have a upper bound. So you know what is the value of entanglement of formation for a maximally entangled. So what we are saying is we have something close to that. So we are able to give you the amount of entanglement, which is very crucial for protocols. So it's not CHSH Bell, because CHSH Bell just tells you whether something is entangled or not. Anything above 2 is entangled. So what is the significance of 2√2? That it is maximally entangled. So similarly, 0 to 1.
Yeah, so I would like to go back to your first part where you are generating pairs of qubits.
Yeah.
So I would like to, if you can clarify again exactly what are those qubits made of?
Mhm.
And second, the next question is, have you thought about what can you do with that?
Yeah. No, that is what I said, that is what we're now thinking about. So first idea was to see if we can make qubits
What are you
this way,
thinking?
whether it at all works or not. So what we have done is we have actually, shaped the pump beam, right? So in down conversion process, you have a pump beam which gives rise to nonlinear interaction with the crystal that gives rise to the pair of photons, among other, a lot of it is classical. So the only pair of photons is 1 in 10 to the 8 or 10 to the 10. So now what we are doing is that instead of using a Gaussian pump, we are using a structured pump. So the structure is, in this case, a triple aperture structure. So now these three, so there are only these three places which have the possibility of the photon, and the rest of it is opaque material, right? That is how you create this. So you have these three structure, three Gaussians in some sense, because anything is a little bit spread out. It's not delta function. So now this guy goes and hits the crystal. It gives rise to, again, the pair of photons, which instead of being Gaussian, as they would have been otherwise, carry this structure through. So what this means is that the photon has is in a superposition of three spatial locations, this, or this. Similarly, on this case, this, or this. So these three spatial locations, as they're called spatial bins, to have this time bin analogy, which you know. So you have these only three possibilities, or 4 or 5, depending on what you're doing. And so these three spatial locations are in a superposition till you actually measure. So you don't know which one it has gone through. So this gives you the 0 plus 1 plus 2, alpha 0 plus beta 1 plus gamma 2 state. So this is your Q tree. This is your Q tree. Then,
Right.
of course, we did the correlation, which.
Right. So, but you have the possibility of changing the separation between the three,
Yeah.
and changing the separation between.
Yes,
themselves.
yes, we have all these possibilities.
But then you can use that. If
We
you
can
have a
use
high
that.
flux, you can use that for something.
For something, which is, of course, something I don't want to necessarily discuss what we are using it for.
Okay.
But then I think you have the hint of what we can use it for. You're
Okay.
saying all the right things. So,
Okay.
but we don't want to complete the sentence. Yeah. Okay. Yeah.
Okay, one last question.
In the negativity part again, so
Yeah.
you have related the entanglement monotones to some correlations that you can measure in your lab, some correlative functions.
Not just in my lab.
Yeah, exactly.
Also in my lab. Yeah.
Yeah. So my question was like, are those functions like, could you calculate them even in other qubit systems? Suppose I have a superconducting qubits, and can I calculate them? Like, is it an experimental specific relationship?
No, it is not, of course. No. So then, of course, that is the whole idea. So this is a test bed for actually telling you that, of course, it's the theory works, and to show that, a proof of principle experiment using photons. But this, of course, translates equally well to your, higher dimensional systems in solid state systems. And that is the idea, that, to come up with a new way in which you can actually substitute the usual tomography measurements by doing these, So mutual information is something which is very well measured in many systems. So you must have heard of mutual information. It's a system agnostic, statistical correlation. So now we are able to measure it in our lab by using certain, for our system, we know what to do. But then, of course, others also know it. So now the idea is that you can use this mutual information to know what is the negativity. So using a perfectly statistical correlation measure to actually show that it has a monotonic, it's an analytic relation with negativity. You don't have to do the whole tomography. And that is the idea of, it's a resource scaling problem. So we can do it with less resources.
Thanks.
Thank you very much. Okay, let's thank Urbashi again.